If your child is curious about artificial intelligence, you've probably hit the same wall I did. Should they start with Python or Scratch? It's not an obvious choice. One is colorful, intuitive, and built for kids. The other is text-heavy, unforgiving, and used by professional engineers at NASA. But here's the thing, only one of them will actually prepare your child for real AI work. My name is Rajiv Patel, and I've spent years testing both with my own kids and dozens of families in our community.
You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you hear in this episode, all the research, data, and the script itself is written and verified by real people on our team. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that. Now, if you've been listening for a while, thank you. Seriously, it's always great knowing there are folks tuning in regularly. And if this is your first time here, welcome aboard. We release new episodes every Monday, Wednesday, and Friday covering the tools, the science, and the strategies that help kids build real STEM skills at home. Let's jump into today's topic.
So let's cut to the chase. Python delivers production-grade AI skills and aligns with what employers actually hire for. Scratch builds foundational logic beautifully for kids around 7 to 10 years old, but it doesn't have the library ecosystem required for real machine learning work. If your child is serious about AI as a potential career path, Python becomes mandatory by around age 11 or 12. This isn't about picking the cooler language, it's about measurable skill outcomes, what hardware you actually need, how these tools fit into a progression pathway, and whether your kid will be ready for internships or university STEM programs down the line. I'm looking at computational requirements, library support for neural network frameworks, and the exact point where Scratch's visual approach stops being helpful and starts holding kids back. Let me give you a quick comparison to frame this. When it comes to AI library support, Python gives you TensorFlow, PyTorch, and scikit-learn. These are industry-standard tools. Scratch has some machine learning extensions, but they're limited and purely educational. For age and skill level, Python works well starting around 10 or 11 if your child can type comfortably and handle abstract reasoning. Scratch is great from ages 7 to 9, even for kids who are still learning to read. In terms of career alignment, Python directly matches 89% of machine learning job postings according to Stack Overflow's 2025 data. Scratch has zero professional use. You will need to transition eventually. Hardware-wise, Python needs at least 8 gigs of RAM for model training and works offline. Scratch runs in a browser or on a 2-gig tablet, but depends on the cloud for machine learning extensions. Cost? Python is free. You just need to invest in decent hardware. Scratch is also free, though some ML extensions require accounts. And here's the big one. Python scales all the way to production work in data science, robotics, and AI research. Scratch hits a dead end around age 11 or 12, and your child will have to migrate to a text-based language anyway. Now, let's talk about the fundamental architecture difference between these two. Python and Scratch operate on completely incompatible paradigms when it comes to AI work. Python's text-based syntax connects directly to NumPy arrays, tensor operations, and GPU acceleration. That's the computational foundation of modern machine learning. When a child writes model.fit x_train, y_train in Python using scikit-learn, they're invoking the exact same library that a NASA engineer uses for satellite image classification.
Scratch's block-based interface turns computation into visual metaphors. That works great for sprite animation and game logic. It falls apart when you're teaching AI because machine learning requires manipulating multi-dimensional arrays, tuning hyperparameters across dozens of variables, and understanding backpropagation. Those concepts don't compress into drag-and-drop blocks without losing the essential nuance that makes them meaningful. The lifelong kindergarten group at MIT created Scratch. They designed it for ages 8 to 16 to teach computational thinking, not domain-specific toolchains. Scratch ML extensions like ML for Kids provide supervised learning demos, image classification, text sentiment analysis, but they run on remote servers with pre-trained models. A child doesn't build or train the neural network. They label data and watch results. That's data entry, not AI engineering. I tested this boundary with my own kids. My 9-year-old built a Scratch project that recognized hand-drawn shapes using ML for Kids. She could explain the interface, but she couldn't tell me why her training data size affected accuracy or what a confidence score represented mathematically. 6 months later, using Python and a Raspberry Pi 4 Model B with 8 gigs of RAM, check the link below to see the current price, she trained a convolutional neural network on CFAR-10, adjusted learning rates, and graphed loss curves. She now understands overfitting because she's seen it happen in TensorBoard logs. That's the difference. Python has a steep initial learning curve. Syntax errors, terminal commands, environment setup, it's a lot at first. But those early struggles pay skill dividends that Scratch simply cannot. By age 12, a child fluent in Python can contribute to real AI projects that involve actual datasets, version control, and reproducible results. That's the triad that defines employable AI literacy in 2026. Moving on to hardware, software, and connectivity requirements, Python-based AI education requires an investment beyond a Chromebook. Training even lightweight models, logistic regression, small neural networks, demands 8 gigs of RAM minimum, 16 preferred. My test rig is a refurbished Dell XPS 13 with an i5 processor and 16 gigs of RAM. It runs scikit-learn, TensorFlow Lite, and Jupyter notebooks without thermal throttling. Cost is around $400 used in 2026. Python runs offline once you've installed it. Download Anaconda or Miniconda, install libraries via pip, and your child can train models without needing an internet connection. That's a critical advantage for iterative debugging. IDEs like Thonny, which is beginner-friendly, or VS Code, which is the professional standard, support breakpoints, variable inspection, and linting. These tools mirror what software engineers use daily, so kids are building skills in an authentic context.
Here's what you actually need for a Python AI setup. Operating system compatibility, Windows 10 or 11, Mac OS 11 or later, Ubuntu 20.04 or newer. Linux offers the best library support. Power-wise, you need a laptop with at least 45 watts. Desktop builds let you add GPU acceleration with NVIDIA CUDA for TensorFlow. Storage should be at least a 128GB SSD. Datasets and model checkpoints eat up space fast. Peripherals are helpful too. An external webcam for computer vision projects, a USB microphone for speech recognition experiments, and expect the hardware to last 3 to 5 years with proper cooling. SSD failure is the main risk. Scratch operates in a browser or via an offline desktop app on Windows, Mac OS, or Chrome OS. A $150 Amazon Fire tablet runs Scratch 3.0 well enough for basic projects. Machine learning extensions require internet and a free account with services like Machine Learning for Kids or Teachable Machine. These platforms impose rate limits. My daughter hit a 100 project cap that required email verification, which is an unnecessary friction point for a 10-year-old. Scratch's low barrier to entry collapses around age 11 when kids run into its block limit, approximately 300,000 blocks per project, and performance starts degrading with complex logic. Python scales infinitely. A high schooler can run the same code base on a Raspberry Pi, a cloud GPU instance, or a university supercomputer. Scratch offers no equivalent portability. For parents building a home STEM lab, Python justifies the hardware cost because the same machine supports CAD with Fusion 360, data analysis with Pandas, and robotics programming with Arduino or Raspberry Pi. Scratch delivers one skill. Python delivers a platform. Now let's talk about measuring skill acquisition and career readiness. I evaluate educational tools against a single criterion. Does this prepare a child for tools used in actual hiring workflows? Python dominates 83% of data science job postings and 76% of machine learning roles, according to Indeed's 2025 skills analysis. Scratch appears in 0 professional contexts. Here's what Python teaches: syntax discipline,
indentation errors, type handling, and debugging skills that transfer to JavaScript, C++, and Java. Library ecosystems, understanding import statements, package managers like pip and conda, and dependency management. Version control readiness. Python projects integrate seamlessly with Git and GitHub, which is the industry standard for collaboration. Data manipulation. Pandas data frames are the entry point to SQL, Excel automation, and business intelligence tools.
Here's what Scratch teaches: algorithmic thinking, loops, conditionals, variables, foundational concepts but language agnostic. Event-driven programming, which is useful for game design, but less relevant to AI workflows. Immediate visual feedback, which is motivating for ages 7 to 9, but creates dependency on instant gratification. The gap becomes measurable around age 11 or 12. A child who learns machine learning using Python can, within 12 months, build classifiers that predict housing prices, sort images by content, or generate text with Markov chains. These projects belong on a high school resume or college application. A Scratch portfolio, regardless of complexity, signals beginner to admissions committees and employers. I've watched this play out in hiring. Our engineering team evaluates intern candidates aged 16 to 18 based on GitHub repositories. Applicants with Python projects, even simple ones like a Jupyter notebook analyzing sports statistics, demonstrate self-direction and tool fluency. Scratch projects, when submitted, indicate the candidate hasn't progressed beyond middle school curricula. This isn't elitism, it's marketplace reality. The skill half-life in AI is approximately 2.5 years, according to IBM's Skills Gap Report from 2024. Teaching Scratch to a 12-year-old in 2026 means they'll need to relearn Python by 2027 or 2028 to stay relevant. That's a wasted cycle. For concrete progression, a child should spend 6 to 12 months in Scratch from ages 7 to 9, then migrate to Python by age 10 or 11. By age 13 or 14, they should be working in Jupyter notebooks with version-controlled repositories. That's the pathway to internships, competitive programs, and university STEM tracks. Let's talk about cost of ownership and ongoing requirements. Python's total cost: $0 for software, $400 to $800 for adequate hardware, 0 subscriptions. Once installed, a child owns the toolchain permanently. Libraries update via pip install -- upgrade. The core language is backward compatible for years. This is a one-time investment with indefinite skill returns. Scratch, 0 for the platform, $150 to $400 for compatible devices, potential costs for third-party ML extensions if rate limits become restrictive. The hidden cost is opportunity cost. Every month spent in Scratch past age 11 is a month not building Python fluency. Neither requires consumables, but Python benefits from supplemental resources. Books like Python Crash Course by Eric Mathis run around $30, or you can read Automate the Boring Stuff with Python free online. Datasets are available from Kaggle, UCI Machine Learning Repository, and Google Data Search, all free. Cloud Compute, Google Colab offers free GPU time, AWS Educate provides credits for advanced projects. Scratch's ecosystem consists largely of free community tutorials. Quality varies. I've found most Scratch AI tutorials focus on recognition demos rather than underlying principles. Kids learn to click buttons, not to reason about model architecture. For a family committing to long-term AI education, Python's front-loaded learning curve yields compounding returns. My children now debug each other's code, contribute to open-source projects, and participate in Kaggle competitions, activities that build resumes and network capital. Scratch offered no equivalent trajectory. Now, expandability and integration with other STEM domains. Python integrates with every corner of modern STEM. A child learning Python for AI simultaneously gains robotics skills. MicroPython runs on microcontrollers, and Python interfaces with Arduino via PySerial. 3D printing? Python scripts generate OpenSCAD models, automate slicer settings, and process STL files. Data science? Matplotlib, Seaborn, and Plotly teach visualization, which is applicable to any quantitative field. Web development? Flask and Django enable full-stack projects, connecting AI models to user interfaces. This cross-domain utility justifies Python's complexity. Learning one language unlocks multiple pathways. My son built a home automation system that uses a TensorFlow Lite model to recognize family members via webcam, triggers relays via GPIO pins on a Raspberry Pi, and logs data to a SQLite database, all in Python. That project touches AI, hardware interfacing, databases, and embedded systems. No Scratch equivalent exists. Scratch integrates with Lego WeDo and some robotics kits, but these connections feel bolted on rather than native. You're still constrained by Scratch's block vocabulary and cloud dependency. For parents planning a progressive STEM learning path, Python serves as the central hub. It connects AI learning kits, renewable energy data analysis, and computational modeling. Scratch functions only as an on-ramp, not a destination. So who should choose Scratch? Scratch fits children ages 7 to 10 with limited typing fluency who need confidence building before text-based syntax. If your child struggles with abstract reasoning or sustained focus, Scratch's immediate feedback loop maintains engagement. If they need visual confirmation of logic flow, blocks make dependencies explicit. If they attend a school that uses Scratch in the curriculum, alignment reduces cognitive load. If they show interest in AI but lack foundational programming exposure, Scratch is a safe starting point.
6 to 12 months in Scratch builds mental models transferable to Python later. Pair it with screen-free coding toys for children under 7. Scratch is not a dead end if you treat it as temporary scaffolding. My daughter built Scratch projects from ages 8 to 9. Then we migrated her to Python at 10. She retained the algorithmic thinking, loops, conditionals, state machines, while discarding the block interface. That's the intended use case. Who should choose Python? Python belongs in the hands of any child aged 10 or older with typing fluency, 35 words per minute or more, and a desire to build production-relevant skills. Choose Python if your child wants to participate in Kaggle competitions, science fairs, or hackathons. All require text-based languages. If they show interest in robotics, data science, or back-end engineering, Python is the common thread. If they need portfolio projects for competitive high schools, STEM magnet programs, or college applications, Python is the answer. If they've already exhausted Scratch's learning ceiling, typically 12 to 18 months of active use, it's time to move on. Python demands more parental support initially, installing libraries, troubleshooting path errors, explaining import mechanics, but that support scales down as competence grows. Within 6 months, most kids debug independently. Within 12 months, they're reading documentation and adapting Stack Overflow solutions. For children aged 11 and older, skipping Scratch entirely is viable. Use Thonny IDE with simplified tutorials, focus on immediate output like print statements and Matplotlib graphs, and defer complexity like classes and decorators until later. Let me answer some frequently asked questions. Can a child learn AI in Scratch without ever switching to Python? No. Scratch's ML extensions provide surface-level interaction with pre-trained models, but don't expose the mathematics, optimization algorithms, or neural network architectures that define machine learning engineering. A child using Scratch learns to label training data and interpret results, valuable as an introduction, but insufficient for building, tuning, or deploying models. By age 12, serious AI work requires Python, R, or Julia. Scratch has no professional analog and no pathway to advanced topics like reinforcement learning, transformer models, or GPU-accelerated training. At what age should we transition from Scratch to Python for AI learning?
Age 10 to 11 marks the optimal transition window for most children, contingent on typing fluency, 35 words per minute or more, and comfort with abstract reasoning. Earlier transitions work for accelerated learners. Later transitions, age 12 and up, risk compressing Python fundamentals into an already crowded curriculum. Monitor your child's Scratch projects. If they're hitting block limits, seeking workarounds for performance issues, or expressing frustration with interface constraints, they've outgrown the platform. Transitioning too early creates syntax frustration. Transitioning too late wastes skill-building time on a non-transferable tool. Do we need expensive hardware to teach Python-based AI to kids? No, but minimum specs matter. A laptop with 8 gigs of RAM, a dual-core processor, and 128 gigs of storage runs scikit-learn, pandas, and TensorFlow Lite adequately for educational projects. Expect around $400 to $600 for refurbished hardware meeting these specs in 2026. Avoid Chromebooks unless you're comfortable enabling Linux mode, which adds configuration complexity. GPU acceleration with NVIDIA CUDA benefits deep learning, but isn't required for the first 12 to 18 months of learning. Cloud notebooks like Google Colab offer free GPU access for experimentation. The real cost is time, helping children install Anaconda, troubleshoot dependencies, and understand terminal commands, not hardware. Bottom line, Python versus Scratch for teaching AI reduces to timeline and intent. Scratch serves as a 6 to 12-month on-ramp for children ages 7 to 10, building algorithmic thinking without syntax overhead. Python represents the industry standard tool for machine learning work, mandatory by age 11 or 12 for any child pursuing AI literacy beyond hobbyist experiments. The hiring data is unambiguous. Python appears in 83% of data science roles, Scratch in 0. A 13-year-old with a GitHub repository of Python projects demonstrating neural network training, data visualization, and API integration holds measurable advantage over peers with Scratch portfolios for internships, competitive programs, and university admissions. Treat Scratch as disposable scaffolding. Treat Python as infrastructure. The sooner a child transitions to industry-standard tools, the sooner they build skills with compounding career returns. We've documented this progression across dozens of families. The pattern holds universally. Text-based languages, particularly Python, correlate with sustained STEM engagement and workforce preparation. Block-based platforms correlate with elementary school proficiency that plateaus by middle school. Choose based on where your child is now, but plan for where they need to be in 24 months. That destination for AI work is Python. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. I know your time is valuable, and I'm glad you spent part of it here. New episodes drop every Monday, Wednesday, and Friday, so there's always something fresh coming your way. If you found this one useful, I'd be really grateful if you could leave a 5-star rating and write a quick review. Honestly, it makes a huge difference. It helps other parents who are searching for this kind of guidance actually find the show. And if you haven't already, go ahead and subscribe or follow so you get notified the moment a new episode goes live. Thanks again, and I'll see you next time.